take a couple more minutes to introduce a concept, which once introduced, I should take it to the conclusion, but I will do that tomorrow. It's a very important concept that I'm going to introduce now, which is wedge stability for friction only case. The thing is, it has been seen that if you calculate the factor of safety by putting cohesion equal to 0 and removing water, which means no water, no cohesion, you'll get some factor of safety. That factor of safety can be very quickly obtained. Equation for that factor of safety comes to this. See, the factor of safety equation is equation 9. I'll take you to equation 9. We'll again repeat this information tomorrow, don't worry. Let's go to equation 9, but I want to leave you with this thought. In this, if you remove cohesion, CA and CB 0, so this factor is completely 0, gone. Reduce water to 0, which means there's no role of gamma W here. So this factor is 0. So what you're left, and this also, you're left with A tan phi A plus B tan phi B. Just this. So let's fast forward to, for friction only case for dry slopes, which means no cohesion, no water, the factor of safety becomes this. In this, we have seen the equations for A and B. Are they reproduced here? No. A and B. I have to go back once again. The equations for A and B are these. You can see they're all angles and no dimension, A and B. So this equation has no dimension. It's a these A and B are dimensionless vectors. Okay, they have only angles. So which means A and B depend on the dips and dip direction of the two planes, plane A and plane B. Now I am introducing that concept. In this factor of safety, there is no role, absolutely no role of the slope dimensions and height and angle, etc. You can cut the slope at 40 degree or 90 degree. You can cut the slope of 100 meters high or 10 meters high. The factor of safety does not change because those things are not there in factor of safety. How interesting. No role. Okay. Now this concept becomes very useful, and which is what I'm going to tell you tomorrow. Okay, this, and I'm going to link the whole things to the practical side of things.
And today we are going to pick up the threads from where we left, which is the presentation on wedge failure. We couldn't complete it yesterday because the time was up, and also we were entering as an important part of the presentation, which is how do we apply the knowledge that we have gained for a quick check for the wedge failure possibilities without spending too much time and resources on checking every meter of the slope. Okay, so let's get going with that. And this was the last slide we saw, okay, in which, leading to the slide, just to give you a quick recap, we were looking at the simplified approach for finding a factor of safety. Simplified means no water and no cohesion. So only friction and no water case, in which, if I go back, this was the factor of safety. So if we could know factors A and B, we would be able to quickly find out the factor of safety. And if this factor of safety, this simplified factor of safety, is above 2, then we are okay. Because time and again, people have carried out analyses, and they have found that this friction only factor of safety, which is this factor of safety, whatever value you get for this, for the worst condition, one of the most severe condition for that slope, the factor of safety is not less than half of it. So if you get a factor of safety from the simplified equation, 2 or above 2, you are okay. So for a long alignment, other than leaving everything to the mercy of nature, at least let's take a calculated risk. I mean, there's hardly any risk. A calculated risk is not a risk really. And so you know that there are certain stretches of the alignment where you need to spend more resources, more time to identify such resources, carry out this simplified analysis. And wherever you get the factor of safety, which is less than 2 with this simplified approach, then of course for that particular stretch, you carry out more detailed analysis. So let's see, how do we quickly check this? As I said, you know, of course, the phi A and phi B values. That's it. And for the two planes, and A and B factors. There are charts developed for A and B factors. If you go back briefly,
these equations for A and B, the equations depend on certain angles. Okay, basically the dip angle and dip directions of the planes. So if we could know the range, so the idea is that to use these charts, for example, if the difference between the two planes is 10 degrees, then you use this chart. If it is 20 degrees, you use this chart. 30, you use this chart. Oh, 30 is not shown here. Why? It should have been shown here. Ah, okay, I know. You know what happened? I told you in the beginning of the course, my computer crashed and I'm yet to get it back. So I perhaps had an old version of this presentation saved, so that the difference 30 is not there. Doesn't matter. The document that I'm going to send you will have that. These charts, how do we use these charts? Okay, so let's go back to the same example that we were discussing yesterday, for which we had this complicated looking Stereonet. Just to give you a glimpse of that Stereonet. This is what we were discussing yesterday. For this problem, suppose we go forward, and if you remember that this example, for the worst condition, it was mentioned that the factor of safety obtained was 0.62, zero cohesion and maximum water pressure. That's the worst condition. Now, for the friction only case, that's simplified formula. For the same problem, the values were given yesterday, phi A, phi B values, etc. If you carry out this factor safety analysis, you will get 1.24. So which means for the worst condition is exactly half of that. Okay. So that's what the conclusion is. There are many calculations. It's not just one sample one here, but people around the world have carried out this calculation, and it is concluded now that as long as you get a factor safety more than 2 with friction only factor safety, you're okay. Okay. So we'll look at an example later in this presentation today. Okay. Now, as I mentioned that when you are designing a cut slope for projects, that these friction only charts or the formula that you saw, they give you all the information that you need for the preliminary design and planning of the project. So you can, at that stage, you can identify potentially unstable wedges or the stretches of the alignment which would require more analysis and therefore more investigation. So that's how you plan, rather than either doing extensive investigations all along the alignment and worse, not doing it at all, thinking that, oh, who will carry out so much investigation? We'll go by experience. So this is a good way out of that. But that's during the preliminary stage and the planning stage. But during construction also, these charts and that equation, simplified factor safety, can be used effectively to make a rapid, quick check of the stability conditions as you are excavating the slopes. You're building the alignment. You know, for example, it's a common practice. If not, then it should be the common practice that as excavation is in progress, there are geologists who are mapping the excavation face, because now the rock mass is getting exposed. You're looking at the actual condition. So you get those conditions, you see the phi, the dip direction, dip value, etc. You can quickly check the factor of safety based on that. And we'll just see one example how to do that. Okay. And if you see that, okay, factor of safety is more than 2, don't worry too much about it. But if it is less than 2, then guys, hold on. I need to carry out more detailed analysis, right? So it's kind of a design as you go philosophy. Okay, so here's an example coming up now to illustrate the use of these friction only charts that you saw and that equation, in which you basically charts will help you get those factors A and B. Okay, so A has the flatter dip. Usually flatter of the two planes is assigned A or 1. But this day and age, people don't follow the customs. You know, anything goes. But traditionally, plane A and plane B means A is the flatter of the two, or plane 1, plane 2, 1 is the flatter of the two. That's easy, you know, if you follow this concept throughout the project or throughout your organization. So the first step, now we are looking at the example. The first step is to calculate the absolute values of the two differences between the two planes, differences in their dip directions and differences in their dip values. Okay, so if you look at table 3, which pertains to that project, you have two planes that are in question, A and B. The dip difference is 30 degree, 40 degree and 70 degree, 30 degree. And the dip direction difference is 120. And those are the phi values. That's all you need, phi A and phi B. Now, these differences then can be taken to those equations or to those charts which are based on those equations. I'm going to take you to those charts. Let's imagine that it is 20 degree, because we have the chart for 20 degrees and the dip directions are 165 and 285. Difference is 120. How do we use them? If you go to chart for dip difference 20 degree, you want to calculate the value of factor A and factor B. Okay, for factor A, you look at the dip of plane A, but before that, you look at the difference in dip direction. So we have chosen the charts for 20 degree dip difference. Now we look at the dip direction difference. That is 120 degree, 120. Now for 120, you go up like this and see where it meets the curve for the dip. What was the dip of the first angle? I think 40 was the dip, sorry. 40. So it intersects it here at 40. Corresponding value of A is 1.5. I think it matches with the 30 degree dip, 1.5. So A is 1.5. For B, for 120 degree dip direction difference, the dip of this particular plane is 70 degree. So sorry, if you go to 70, oh, my eyes are not supporting. Yeah, it's about what, 0.6789, about 0.7. So 1.5 and 0.7. Let's see how close they are to the 30 degree chart. Oh, the same, exactly same. The values of A and B are 1.5 and 0.7 respectively. So for 20 degree and 30 degree chart, there's not much of difference as far as these values are concerned. Now, so we got the values of A and B. Now the factor of safety is very simple. We know the values of phi A and phi B, 35 and 20. We know the values of A and B, 1.5 and 0.7. We go back to equation 14, which is this simplified factor safety. 1.5 multiplied by 10, whatever, I've forgotten the value. B, this is 1.7 multiplied by 10, whatever be the value. And the factor of safety obtained is 1.3, which means for a friction only situation, no cohesion, no water, 1.3 is a low factor of safety. Because for the worst condition, if the worst condition was to happen on that slope, this would be 0.65. Now, it is not necessary that your slope will necessarily encounter the worst condition, but to be on the safest side during the planning stage, if this is more than 2, don't worry about it. We'll worry about this when we come to the excavation, because during excavation, actual construction, you would again have a relook at this and then make a decision based on the actually exposed rock mass. You're much closer to the reality at that stage. It's so vital to have your engineering geologists and the structural geologists, of course, and the designer involved right through the construction because of these reasons. Let's take a practical example, which during the route location study, one of the important initial planning requirements is to the location survey, or it's in various countries call it differently, like route location study or route location survey. Study is a better word, because it's not only the survey but many other things that you do for a proposed highway. The engineer who was tasked with looking at the layout or finalizing the layout, called the layout engineer, he requested some guidance to be provided to him that what could be the maximum safe angle at which the slopes could be cut. Now, this is a very important question and very frequent question which everybody wants to know the answer of at the initial stages. Okay, what is the angle? Because everything else is related to it. Your project planning, your cost, time, and everything, the equipment that you mobilize, the land acquisition, the environmental, the relocation of people depends on that angle. So much hinges onto this decision, that angle. So rest of the things can be decided later, but the first thing is that what is the maximum safe angle? Because everybody wants to cut it at the steepest angle. Steepest angle solves many problems, because you have to remove less rock and therefore less cost involved, less time involved, less mucking, less dumping areas, less environmental problems, less relocation in case there are people or people's properties up there, less movement of utilities. You may have these electricity transmission towers, for example, and relocating them is a huge task. As you know, in those inaccessible area, how these guys using choppers and helicopters install those massive towers. It's a big decision, and you know, just managing these things, which may be put under the enabling works, can delay the start of the project by 2 to 3 years, depending on where you are. And so all of that can be reduced. There could be wildlife issues or whatever. So this angle, it all boils down to this angle. And therefore it boils down to you, the people who are there to advise on what is the maximum safe angle which may be used. To answer this question, it's not a difficult thing, provided the geologists on the site have done extensive geological mapping. So in this case, the geologists had found that there are 5 sets of discontinuities. 5 are a lot, okay, through which the highway will pass. The dips and dip directions of these discontinuities are shown in the next table, which is coming on the next slide, together with the variation. Obviously, we'll expect variation because not all joints are the same. In one joint set, you have several variations. So within one joint set, you have variation. And that is why on the Stereonet, remember, when we plot the poles, there's a concentration. All the poles in one joint set do not overlap each other. They're close to each other because of the variation. And we look at that concentration. So if you look at that pole plot here, these are the values of dip direction. Those are the variations. Let's look at the pole plot. Those are the pole plots. Don't look at the lines as yet. Just follow what I'm telling you. These 5 joint sets or discontinuity sets are shown in terms of their pole plots, these inverted angles. Okay, 1, 2, 3, 4, 5. Now I'll tell you something very interesting, which is not mentioned in this presentation, which is already with you. Look at these shapes, different shapes. Why? Any idea? 2, for example, looks pretty different from others. It's very oblong, elliptical kind of stuff. It's very long along the primitive and flat perpendicular to the primitive. I'll give you an idea. What do we measure from the primitive? We measure the dip. Okay? And along the primitive, like this, we measure the strike or the dip direction. Remember? So clearly, the variation in the dip directions of those individual joints which are part of this set, the variation is much larger as compared to the variation in dips. So let's go back to the table and check for number 2. You can see the variation in dip is plus minus 6 and here is plus minus 15. So wide variation. That is why you have this shape. 1 and 4 and 5 are pretty circular. 1, of course, plus minus 2, plus minus 2. 5 plus minus 4 plus minus 2, not much difference. 4 also. That's why they're circular. Okay. So that way you can find out an interesting aspect. Anyway, so also shown on this stereo plot or Stereonet are the corresponding great circles. That's what we do when we do kinematic analysis. First, we plot the poles. Secondly, following using the contour option, we find out the clustering, which has been found out in this case. And then for each of those clusters, we plot corresponding great circles. Remember from kinematic analysis. That's what has been done here. So for this concentration 1, this is the great circle in the opposite quadrant 1, it is mentioned. For 2, that's the one. For 3, that is the great circle. For 4, the great circle would be here. This is the one. And for 5, that is the one. For 5 is here. So that's the great circle. Right. Now let's look at where do these great circles intersect. They are intersecting at these locations, but you know, these are the mean great circles. If you plot the great circles for all of these, all the points that are there, right, you will have thousands of great circles intersecting. So this dashed line shows that all the intersections for all the individual joints taken together, all the intersections lie in this zone. So this can be the zone of instability. That's where the intersections take place. For the average or for the mean great circles, those are the intersections. And these values which are mentioned in these circles are the factor of safety values. It's not the fiction only factor of safety, it's the actual factor of safety. Okay, and you can see that some of these values are dangerously low, except perhaps 1.5, which means collapse is imminent if you draw this. This has been left out of this part because anything beyond that will have a dip less than 30. 30 is the friction angle in this case. So from the primitive, this is 30 degree. Anything beyond that will have a dip of less than 30 degree. Friction will not let it slip. That is why this has been left out, this point. So this is the unstable zone, right? That's what is mentioned here. Yeah, already explained. So the collapse will take place. So what is the solution for these things? The solution for these situations is that I told you that one of the smartest ways of making your slope stable against sliding is cut the slope at the same angle as the line of intersection, or in the case of planar failure, cut the slope at the same angle as the angle of sliding plane. Then daylighting will not happen. So the solution is that you cut it flat to that angle, okay, for such things, right? Otherwise you have to spend a lot of resources, a lot of money on putting rock boards, etc., etc. Okay, so in this case we are not designing. The alignment engineer asked a question, what is the maximum safe angle? So to answer that question, you can say the maximum safe angle is only as much as the dip of the line of intersection, which is pretty flat in this case. Okay, for those intersections where the factor of safety is more than 1 or between 1 and 2, you can carry out detailed analysis for these areas, for this, for example. Okay, otherwise you don't have to do detailed analysis to advise the alignment engineer on this. Okay, now we can actually go a little more than that and use the same stereo plot to find out the maximum slope angle in any dip direction. So you can rotate, you look at all the directions of the cut slope, dip direction, in such a way that unstable zone is avoided, like this. You can have various options. The cut slope is in your hand. The joints are not in your hand. So you can have these great circles, all of these for different directions of cut slope. All of these are avoiding the unstable zone. So you can rotate and find out those great circles of the face which are not going through this unstable zone, all of them. Now, if you look at this, just opposite to them, for example, take this where I'm running my cursor now, this one. Exactly opposite 62 degree. 62 degree is the dip of this. It's mentioned here just for the ease of understanding. That is 62 degree. Now, if you look at this, this will give you this dark line here. On the north face, if you make the alignment east-west, on the north face, you will get the maximum angle is 85 degree. Out of all these angles which pertain to these which are the dip angles for all of these great circles, that's the maximum 85. So you choose this because the question asked is what is the maximum safe angle? On the north side, you can cut it at 85 degree. Good angle, pretty steep. On the south side, because this unstable zone is pretty close to the primitive on this side, so you get low values. So on this side, opposite this, you get the maximum value. On this side is all 30 degree actually. So you choose this. So on this side, you cut it to 30 degree. On that side, you cut it to 85 degree. So something like this. Your highway would look something like this. 85 on that side, 30 degree on that side. This is the maximum safe angle. Now, this is for preliminary design. Of course, one can choose to cut it at a steeper angle with detailed analysis, reinforcement, etc., drainage and whatnot. Okay, so this is how you can look at it at the initial stage of it. Now we have seen that you rotate all these things. Now you can see on the using the dip software, you can rotate. You can find out that which direction will give you the best angle, avoiding this, if that kind of thing is possible. Sometimes it's possible if you're taking alignment through a stretch of a rock which is not very long, and you can perhaps take an angle, make an angle, or do something to minimize your length through these. All those decisions can be taken. Okay, so I think with that we come to the end of this presentation, which we should have finished yesterday. And now is the time to, with the knowledge that we have gained, let's see how we can actually design some or how we can actually use the software. Okay, so with that background knowledge, and you see, you might be wondering that we didn't need all this knowledge, but you need when you are stuck and you really need to go into the fundamentals, then this knowledge will be very useful. Otherwise, software are very user friendly, as you saw yesterday also. So the danger with these software is that you get into a false sense of belief that I know everything. But it's so important to know the fundamentals, to know the subject behind it. That's what we have done. So now we go to the software, and for which I'm going to launch the software.